Alright, today we're going to look at how we can handle certain quadratic equations where the solutions are not necessarily rational numbers, where they could be square roots that don't come out evenly, and they're not fractions of integers and so on. Some of these will turn out to have rational solutions. Others will have irrational solutions in which will have square roots of certain values. And that's why we looked at simplifying square roots in the concept bite worksheet that we worked on in class today. But in this section, these first four examples, you will notice that there is no x term. There's only x squareds and constants. So one thing you can do when faced with this type of situation is to get the x squared by itself first, and then take the square root of both sides. So, for example, in example A, we're going to look at just getting the x squared by itself first. So in order to do that, we're going to subtract 10 from both sides first. So we're left with 4x squared is equal to 36. When we subtract 10, then we're going to divide by 4. So then x squared is equal to 9. And when we take the square root of both sides, and again, there are two numbers that you square to get 9. One of them is positive 3, the other one negative 3. And those are the two solutions to this equation. In B, we're going to do the same thing again, except this one will have actual irrational solutions. There will be a square root that does not come out evenly in this case. First thing we do in this one is we want to get the x squared by itself by first adding the 5. So 3x squared is equal to 35. Sorry, 25 plus 5 is 30. And then we divide by 10, or divide by 3 to get an answer of 10. There we go. So x squared is equal to 10. Now, there is no integer that you square to get 10. However, it is a real number. The square root of 10 does exist. If you put that into your calculator, you would get a decimal of 3 point something. It would be a decimal that never ends and never repeats. And once again, we just want to make sure that our solutions are precise and exact. So once again, there are two numbers that we square to get 10. So we have the positive and the negative. And we just leave that as plus or minus the square root of 10. And we just leave it like that, keeping in mind we have two solutions. Positive square root of 10 and the negative square root of 10. In the next one, once again, getting the x squared by itself, we have 7x squared is equal to 35 once we add 10 to both sides. And then dividing by 7, we have x squared is equal to 5. And finally, taking the square root of both sides, again, 5 has two square roots, positive and a negative, and it's something that does not come out evenly, so we just leave that as a square root of 5. So plus or minus the square root of 5. And finally, the last one, getting the x squared by itself, we have 2x squared. When we subtract 9 from both sides, we get 2x squared is equal to 4. And then when we divide by 2, x squared then is equal to 2. And again, there are two numbers that we square to get 2. One of them is positive, the other one is negative. And the exact values are plus or minus the square root of 2. Now in these we can do the same thing again, but one thing that we are told is that this and this turn out to be perfect square trinomials, which means they are the square of a binomial, where if we tried to factor those on that side, we would get factors of 4 that add up to 4 are 2 and 2. So we'd have x plus 2 times x plus 2, or x plus 2 squared, which is equal to 25. Now this might look familiar when we were trying to find x-intercepts of those graphs in vertex form. So again, we're squaring some number to get 25. So that number is either 5 or negative 5. And solving for x, x is either equal to, when we subtract 2 over here, we get negative 7 or 3. Now, since we got integers for answers, or rational numbers, what that tells me is that this could have also been solved by factoring. And if we think back to the 4 or 5 section, we could have subtracted 25 from both sides, so x squared plus 4x minus 21 is equal to 0. And then what factors of negative 21 add up to 4? Well, positive 7 and minus 3. So that means that x plus 7 would equal 0, or x minus 3 would equal 0. Solving each of these for x, we get x equals negative 7, or x equals 3. And we got the same answer with both methods. B is also one kind of like that. We could use either method to solve this. Once again, factors of 49 add up to negative 14, well, x minus 7, x minus 7. So that's x minus 7 squared. That's what it means to be a perfect square trinomial, is that it can be factored to a binomial square, and that's equal to 36. So we are squaring a number to get 36. Well, so then that number needs to be either 6 or negative 6. And getting the x by itself in the middle by adding 7 everywhere, we have 1 is equal to x, which is also equal to 13. So x is either 1 or 13. This one also can be solved by factoring if we subtract 36 right away. And factors of 13 that add up to negative 14 are negative 13 and negative 1. So that means x minus 13 equals 0, or x minus 1 equals 0. So that means x is either equal to 13 or 1, which is what we found there. In the next video, we're going to talk about how to handle it, how to create this perfect square trinomial so that we can solve these for x.